My title for my presentation today is Comparative Analysis of Cohesive Methods in Predicting Intra- and Interlaminar Failure in Cfrp, Carbon Fiber Reinforced Polymer Laminates under the Low Velocity Impacts. And my paper ID is number 34. Let's begin with introduction. LVI means low velocity impact. So it means I focus on the composite laminate. We'll start with what is low velocity impact actually. So actually they have this kind of significant implication for the structural integrity and performance of the composite, because when we apply some kind of impact load, you will see the plate or the composite itself will become damaged, because due to the some kind of very minimum impact, it will also contribute to the some kind of accumulation of damage. So in contrast to the high velocity, because another part of the impact itself, we have two. Either we use the low velocity impact, or we can talk about the high velocity impact. But our concern now is about the low velocity impact, because it relatively occur at the lower speed. It typically is less than 10 meters per second. So for example, if we have the composite used in aircraft fuselage, are routinely subjected to the LVI, which is a multi-impact caused by the collision with the bird, rock, or even ice stone. Because this is something very critical when we talk about the aeroplane, for example, when it fly a little bit higher and it will crash together with this kind of the bird strike, for example. It also can contribute some kind of small damage due to the kind of impact. That's why we call it as the low velocity impact. So to better understand the impact behavior, experiments, of course, are required. However, it's very costly, because to fabricate one specimen, it costs a lot of money, as well as we need to do some kind of testing. And that's why we really crucially need the final element method, because this is the best tool so far for the structural response and damage behavior of the impacted composite laminate, because due to the kind of availability as well as the kind of the cost to run it. Next slide. What is the problem statement? Why we conduct this kind of research? Since that we're talking about the Cfrp composite, it's a very widely used. It's everywhere in the engineering field, because due to the kind of superiority of the properties itself. So either it's a strength to weight ratio as well as the design flexibility. So however, their susceptibility to impact damage remain a significant challenge. So these LVI events, which are often difficult to detect visually, can compromise the structural integrity, because it can degrade the structural integrity, because due to this kind of low velocity impact, and thus reducing the damage tolerance and overall the safety itself. So it is a need, or it is required to study this kind of phenomena using the numerical tool, because due to one is for the kind of cost saving. Second one is kind of very flexible to change in terms of the parametric study as well as one. So besides the use of subjective failure criteria, in this case, I will emphasize on one failure criteria can determine the accuracy, or can ensure that the accuracy of the result can be considered, or can be taking care about it. So in addition, the research offer an alternative research direction, especially in terms of modeling techniques. So we can tailor whatever we need, whatever we want from this kind of analysis. Objective, I have three objectives in this research. The first one is to develop the three-dimensional low velocity impact model. We will incorporate, so I'm already incorporated with this kind of progressive damage model, highlighting about the usage of the Pook failure criteria together with this kind of exponential gradual degradation model. Number two, so we need to validate the numerical model. We are emphasizing or focusing on the cohesive lamination technique. So in our case, we have two types of model that we will use, and we focus on the different impact energy, as well as we can compare with the experimental data. And last but not least, I observe the failure mode patterns together. So we can see that we have 5 types of failure modes that can be investigated here. Right, so now I move into the materials and methods. So straight away, so this is my final element model. This is final element model. where we have three parts actually. So the first one, I have the impactor here. This is the impactor. You will see the material that used here is a HS300/ET223. So this is a carbon fiber reinforced polymer composite material. Using the stacking sequence of, we have a combination of 0 degree, 45 degree, as well as minus 45 degree without application of 90 degree here. In total, we have 10 layers. So this is a 3D, three-dimensional laminate with 10 ply, 10 layers, considering all this kind of stacking sequence. Dimension, actually this is 87.5 times 65 with the total thickness of 3.2 millimeter consideration. So you know it's a 10 layer. So for one layer, it should be around 0.032 millimeter. It's quite small, quite thin. So for the impactor, we have a rigid body. So I treat it as a rigid body impactor using this kind of cohesive, sorry, this is a rigid body, sorry, this is wrong actually. So this is R3, D8. So this is a wrong element type here. With the diameter of the impactor, the bottom one is 12.5 millimeter diameter, and together we have to give some kind of mass. For the impactor is around 2.34 kilogram of mass. For the laminate itself, Cfrp laminate, so these are deformable bodies. It will deform based on the impactor that apply to the laminate itself. So I'm using the C3D8R because this is using the three-dimensional element. Finite thickness cohesive element, because we will implement the cohesive element altogether. I have a 4 cohesive element here. Cohesive element number 1 from the top, and the last one is measured from from the top to the bottom. So cohesive number 4 is the below this cohesive number 3. You will see that this is the finite thickness using the 0.001 millimeter here. Having the friction coefficient, so M to L mean metal to laminate. So we can assume that this is actually from the metal itself and to the laminate when it touch. So the friction coefficient is around, or it's absolutely is a 0.3. So this is can be obtained from the literature. And to run or to solve all this kind of numerical simulation, all the calculation, I will use this. I'm already used this abacus explicit exposure solver because this is kind of dynamic process. Okay. Next, so I'll just show you a little bit on the finite element model for the material properties here. So altogether, actually, I'm using this kind of 16 material properties for the laminate. You will see for intralaminar. So when I mentioned about intralaminar, so this is for the laminate itself. We have 9 properties for elastic, as well as I have 4 plus 3. Yeah, so it means that 7 properties for the strength. This is for intralaminar, as well as for the cohesive itself. I have altogether, we use the 9 material properties for the interlaminar or the cohesive properties, and 1 density parameter just for the dynamic process. All right, so what else? So this is kind of overall. I can say that we start, and then we do the pre-processing 3D finite element model. And then the abacus itself, abacus will calculate the stiffness metric before they have any kind of failure. They calculate the stress, and then once after it calculate the stress, it will check straight away the initiation of the intra or and interlaminar initiation criteria. If it's failure onset, yes, then we will check whether the failure will contribute to the total failure. If yes, then it will stop. If no, then it will degrade the stiffness. Same goes to the failure onset. If no, then it will increase the load, and the cycle will recalculate the stress and again check for the for each iteration. It will check for the new stress, check for the intra and interlaminar criteria as well as everything. And you'll see at the right side here. So this is the abacus explicit framework. So in our case, for this intralaminar, so I'm used this kind of VU mat, which is I have to code it in the Fortran because it's not available in the abacus itself. So using the 3-dimensional Pook failure criteria, as well as using the gradual degradation. And the right side here, this is for the cohesive, is already embedded into the abacus. So I don't need to do anything, just recall for the elimination using the quadratic nominal stress criterion, as well as apply the BK power law here. And then it will run until it stop, and we will get some kind of result after that. So this is a kind of comprehensive study about this kind of intra and interlamina initiation criteria. You see, we have a fiber metric failure. At the same time, it will calculate simultaneously for the fiber and metric failure as well as delamination measure. What happened in the fiber metric failure? We have this kind of equation here. For the fiber breakage, for example, we have it into two terms. F, Ft, T, and C. T represent for the tension. C indicate for compression. So this is the function. You will see there is some kind of the strength property apply here. Same goes to the Poisson ratio for the fiber, Poisson ratio for this kind of laminate. For the metric cracking also, they will check based on this equation, based on the tension and based on the compression. And you will see that this is the diagram for a little bit on how the PUCs determine its own failure criteria itself. And for the delimitation, as I mentioned before, we just input this kind of material properties. So T means for the traction separation value here. We input everything here just to invoke for the kind of failure initiation. So the next task is failure degradation, but I will not discuss here. So when the function achieve unity value here or equivalent to 1, we will degrade the material properties. We degrade the function, everything, according to the gradual degradation that I'm already imposed before here. What else can we discuss? So that's all for the methodology, or sorry, for the research output, what we will gain from all this kind of assessment. So we'll study about the maximum contact force, impaction time, energy absorbed, and then this is for structural response. And for the failure mode, so we observe the fiber breakage. T and C. T means for the tension. C represent for the compression. We investigate for the fiber breakage, for tension and compression, metric cracking for the tension and compression, as well as delineation, because we obtained it from the kind of cohesive analysis before. So I go straight away for the result and discussion. So this is what I obtained, what we obtained actually. So this is for the contact force and impaction time. You will see I have a 3 diagram here produced from the assessment that has been done before. We have an impact energy for the 2 joule, 4 joule, and 8 joule. You will see, and for each case, we will compare with the experiment. So I label as here as a PUC CE. CE means cohesive element because I have 2 approach, using the cohesive element and using the CC mean cohesive contact. You will see for the 2 joule, which is quite very low, you will see that using the CE, which is the cohesive element, is a little bit shaky in terms of the curve. However, in terms of the quality of prediction is more identical or similar with the black one. The dash one is represent the experiment. However, you will see that using the cohesive contact is a little bit of overestimate here. However, a different story with the 4 joule, you will see that using the cohesive element is a bit over predicted. However, using the cohesive contact is similarly or identical with this kind of experimental. And again, in contradict with the 4 joule, for the 8 joule, you will see that both actually the red line here for cohesive element is a little bit on under predicted. However, if we compare with the cohesive contact, is over predicted. So some kind of balance. So I can say that the both simulation approach closely follow the experimental data. Okay, the pattern is there. However, some of it sometimes is over predicted, sometimes is under predicted. And because, however, I can say that due to the impaction time. So if I want to focus on the impaction time, you will see that the greater the increase, the increment of the impact energy from 2 joule into 8 joule, you will see that the impaction time becomes increase. You'll see when it comes to the 2 joule, everything's stopped at the the similar point with the experiment. And if you increase into 4 joule, it increased to the right. So the impaction time is a little bit greater as compared to experiment. And you will see here, a little bit larger as compared to the 2 joule and 4 joule. And in terms of the quality, I will discuss in the next slide. All right, so this is the overall analysis. So you'll see the impact energy from 2 joule up to the 8 joule here. You will see, I can say that I highlight here. So some parts, the cohesive element works better. Some parts, cohesive contacts works better. It's a kind of average. So both simulation approach closely follow the experimental data. Forces and energy observed, you can see that, in terms of the quality, so this is the discrepancy percentage. The ones that I highlight into the red is performance of the cohesive element. It performed well. You will see it performed well in terms of energy absorbed. Okay, cohesive element is performed well in terms of energy absorption. However, can mentions that cohesive contact is performed well in terms of the prediction of the maximum contact force. So it's depend which part we want to concern. If you say that, okay, I want to talk about the contact force, so I think it's better to use the cohesive contact because it will give you better performance, a better result. Or if you want to say, okay, let's talk about this material that can absorb energy more. So things that in terms of the quality, I will use this kind of cohesive. The mesh morphology, so you see that the mesh morphology is based on 8 joule impact only because I won't show it for the 2 and 4 joule. Accumulation of failure, you'll see the metric dominated. So I mentioned in FFT, IFFT, IFFC. FFT is a fiber failure. IFT actually interfiber failure or metric failure. So in tension and compression, you will see here for this kind of accumulation of failure, you will see that metric dominated failure because due to the matrix failure only because there's no signage of a failure produced from this kind of fiber failure. So it's a blue. The red color showing as a total damage. The blue color is the undamaged part. So you will see that you can see from here there is no failure generated from the fiber failure or fiber breakage here. However, we have an accumulation of damage came from or generated from the metric failure IIF. So either in tension or in compression. So no significant effect from fiber breakage. Why? Because it's insufficient impact force to break the fiber. So the metric or interfiber failure zones become larger over the time. You'll see that it keep increasing because this is the time. The time increase from 25 millisecond, 25 millisecond increase up to, so this is the maximum before it rebounds. So 0.024 second. You will see, the propagation of the damage is become from the top increase until it's distribute equally left and right, and after it reach the maximum and once it rebound it remains as it is. It will not distribute after that. So in compression also you see from lower increase up to the certain one and it's maintained it kind of shape itself because it's no longer propagate because it's already in the bouncing stage. For delimitation, for the delimitation damage mode, you'll see that damage morphology is based on 8 joule. Accumulation of failure, delimitation also contribute to the total failure because it weaken the stiffness of the laminate. Delaminated area progressively decreasing towards the bottom. This is from the top. If you still remember from my slide, we have interface 1, interface 4 is from the bottom, interface 1 is from the top. You will see a little bit effect of the damage occur at the interface 4 because it's not enough. And then at the interface number 2, now it's become dominant here. Interface 3 is slowly decreased in terms of delimited area, as well as interface 4 is become smaller. So the reason why it happened is because the orientation and stress distribution within the composite material under the impact, leading to the varying delimitation extend across the different interface. Right, so for conclusion, I can highlight several conclusions here. In the present study, we use the 3D numerical methods models to develop using the Hooke failure criteria. We use the cohesive element and cohesive contact approach. We have this is two approach to promote the diminution effect. Numerical validation shows the good or the good agreement. So well fit with the experiment and simulation. In most cases, the simulated result overestimate the reference value, but certain case we have some kind of underestimate due to the simplification of stacking sequence and contact mechanism as well as the boundary correction. So we are not following the exact from the original publication. We make some kind of simplification just to save the time, just to save the amount of element that used. Metric failure dominate the total failure of the structure, while fiber failure not visible due to the low impact energy applied. And the cohesive contact approach perform better in low impact energy, while the cohesive element achieve or perform well in higher impact energy. So that's all for my research. So if you have any question, I can answer it. So please email me by using this msuaril@uitm.edu.my.